All right, so I didn't give you any emails asking for anything to be talked about during the live stream. That said, there's 3 people waiting in the stream right now, so I'm guessing there are people with questions. So once you catch up, just go ahead and start posting your questions in the comments section. Do remember you got your exam this weekend. It's online just like the others. Next week, though, Wednesday and Thursday is the final exam. The final exam is cumulative. 80% of that's going to come from test 1, test 2, test 3, test 4. New material is going to be electrochem and the nuclear. You're going to notice when the homework opens up, there's only 8 assignments. It's not a wide breadth of material. The hardest part is actually going to be doing the balancing the redox reactions. It is challenging. Unfortunately, the homework is not representative of the final. It's a lot harder. So I kind of only have a finite number of electrochem problems I can really work through. So that keeps the easier ones on the exam and the harder ones on the homework. But definitely, if you look at the homeworks, you go, wow, these are incredibly hard. Yes, they are. It's because I only have a finite pool to play with. I can probably come up with a lot more, but I've generally found it's easier to make a hard problem than it is an easier problem. Now, next Monday, I don't want you distracted focusing on the final. I want you to focus on exam 4 right now. When it comes to the final, I'll talk about it Monday during the live stream. You're also going to, hopefully, it should be in the announcement telling you about the details. 35 questions, multiple choice. You can submit work for partial credit. You need to take it to the e-learning testing center unless you can provide me documentation as to why you physically can't take it. Then we'll set up a different way for you to take that exam. But you do need to schedule the time with the ELTC in order to take the exam. Grades are due Thursday at 5 o'clock. So basically, if you take the exam Thursday afternoon, don't get the grade you want, and go, is there any way I can get a grade boost? The honest answer to you is no, and it's no because I have to submit my grades Thursday afternoon. I don't really have a choice on this. So in terms of requesting higher grades, try to take it Wednesday if you can, and that gives you some leeway for Thursday, but otherwise, there's not really much I can do for you. Lab grades will get finalized next Wednesday because you have the redox lab that's due Tuesday afternoon. It's the last of the lab assignments. There's no lab associated with it, it's just working problems to give you the extra practice because, again, even though balancing redox reactions is like 1 or 2 questions on the final exam, it is the harder concept to understand. But again, we'll go through more details of the final. But the plan Wednesday is to have all your lab grades submitted, all your lab grades posted, all your homework grades posted, everything up but the final exam. This will be Wednesday before the live stream. Again, I want to make sure you have full idea as to what you need to do in terms of the final in order to pass the course. Generally speaking, the final exam is pretty representative of your test average is pretty representative of your grade on the final exam. So that's all the stuff I had to say in advance. I've got the chat window open up here on my left. So if you got questions, go ahead and post them. I'm going to keep the camera on for about another 5 or 10 minutes. If I don't see any questions, I'm just going to turn it off because I'm pretty sure you don't want to sit here and watch me type. But if you have questions, please feel free to ask. These are not lectures. These are not lessons. These are purely office hours. They are here for you to ask questions in advance or ask questions while you're here. If you can go over question test 4, titration curves calculations, as well as question pH and POH from PKB. So I can do both of those. And then classifying salts as acidic and basic. So we'll do the first 2 questions first. Let me bring up the homework. Now the titrations I can answer pretty quickly. I don't really need a homework problem to do it to illustrate these. But with the titration curves, you're going to use 2 things. The neutralization formula and the Henderson-Hasselbalch equation. So on all these homework problems, you're going to see 2 boxes mapped out. And you got the volume at the equivalence point. This is the volume at the midpoint. You're going to be given a pH here and a pH here. So this is pH at the equivalence point, pK at the midpoint. And with all these problems, you're given a concentration of base, a volume of acid, and that should be it. So what you're asked to find from this information: concentration of the acid and the pKa of the acid, and the volume of the midpoint. And the volume of the midpoint here is to make sure that you conceptually understand the volume of the midpoint. So at the equivalence point for a monoprotic, monobasic acid-base titration, which is all we're focusing on, you can definitely do more than that, but it's just Jim Kim. We're only going to go so far with this. For any neutralization formula, we have the molarity of the acid times the volume of the acid all over the reaction coefficient of the acid equals the molarity of the base times the volume of the base over the reaction coefficient of the base. So if we had like a diprotic acid like H2SO4, Va here would be 2. If we had something dibasic like calcium hydroxide, it would be a 2 here. But because we're working with monoprotic acids and monobasic bases, we end up with this formula. So the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. And this statement is true at the equivalence point. So the volume of the base here is the volume at the equivalence point. So if we want to know the molarity of the acid, it's just the molarity of the base, which you're given, times the volume at the equivalence point divided by the volume of the acid, which you're given. Now, the pH here is a meaningless number. You can backtrack out what it should be if you know the pKa of the acid, because there's a formula that connects the pKb of the conjugate base. It's there. You don't need to worry about it. To find the pKa, we're going to use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation says that pH equals pKa plus the log the concentration of the conjugate base over the parent acid. And the thing is that at the midpoint, these two are equal to each other, so this ends up canceling out to 1. So this is at the midpoint. And so at the midpoint, we get log of 1 is 0, so pH equals pKa. So the pKa here is the pH at the midpoint. So it's the pH here. The volume at the midpoint is just simply half the volume of the equivalence point by definition. So the midpoint is the midpoint between 0 and the equivalence point. It's halfway between the two. So for all those assignments, that's basically what you're doing. You're given the molarity of the base, the volume of the acid, and you're given the volume of the equivalence point and these two pHs. To find the concentration of the acid, just take the molarity of the base, which is given, times the volume of the equivalence point, which is given, divided by the volume of the acid, which is given. That'll give you the molarity of the acid. pKa equals the pH at the midpoint. The volume at the midpoint is half the volume of the equivalence point, and this number here is not useful. pH from pOH and pKb. All right, that I'm going to actually have to look at the problem. All right, so for working with bases, it's very akin to how you work with acids, but you're not going to be able to solve for the pH directly. You have to solve for the pOH first, and that's why it kind of pushes you that way to say, okay, find the pOH first. So if we look at the first problem, it's a pOH and a pH of a 0.1 molar solution, 0.2 molar ammonia, 0.0149 molar Cl, and here we're given the pKb equals 4.74. So with the acid equations, you always had this situation where the acid broke apart into an H and a lost an H and you formed a conjugate base. For bases, we always abstract a hydrogen from water. So these are all going to be Bronsted bases. In this case, we're going to get NH4 plus and OH minus. Now, you still need the three things you need to solve any equilibrium equation. So you need your equilibrium constant, in this case it's Kb. You need your expression for Q, which is NH4 plus, OH minus, all over NH3, and you need your IC table. So we're given the initial concentration, 0.2. Again, we're going to assume the hydroxide is effectively 0 and 0.0149. Changes here, minus x, plus x, plus x. So I get 0.2 minus x, and 0.0149 plus x. And you're asked to find the pOH first. And this is just to kind of give you that helping hand. So pH connects to OH minus the same way that pH connects to H plus. The pOH is just the negative log of the concentration of the hydroxide. So if we can find the extent of reaction X, we can take the negative log of that number and that will give us the pOH. The pH is just 14 minus pOH, and you can see this in the Blair diagrams that are on the course website. So if you go under the Lessons 4 course menu, you're going to see something called a Blair diagram, and it'll show you how to interconvert between pOH, pH, H plus, and OH minus. So this is just the way you solve any of the previous equilibrium problems. We've got equals x 0.0149 plus x all over 0.2 minus x. You're going to get a quadratic equation here. Okay, that makes sense. That's putting the equation together for the base. That's what I was missing. Cool. Still going to go through it though. So once you solve for x, you will get a number. Take the negative log of that number. That'll give you the pOH. And the pH, just as a concept check, you're in a base, so the pH needs to be greater than 7. So your pOH here is going to be a small number. That's the basic equivalent of being very basic. The pH, though, should be very high. It should be a 7 for a basic solution. All right, classifying salts as acidic or basic. So to figure out if a salt's acidic, basic, neutral, or it depends, we're going to build a decision matrix. And one part is, does the cation react with water? And does the anion? Yes, no, yes, no. So any salt is composed of an anion A and a cation C. And they will reversibly dissociate and in water when they dissociate into the anion of the cation. Water here is also dissociating into H plus and OH minus. This is the auto dissociation of water. So we have our anion and our cation, and we add water to both of them. The question is, do they react? So with the anion, because it's negative, it's going to react with a hydrogen, so we're going to get some hydrated anion plus hydroxide. So if the anion does react, we will produce OH minus, which would make it basic. Cation is going to react with the hydroxide, which leaves us an H plus, and that's going to make it acidic. But the question is, does it even react? And to do this, we have to look at what's formed. So for the anion, we're going to form a conjugate acid, and for the cation, we're going to form a conjugate base. And the question is, do they form? And what we'd have to ask is, are these strong? So there are 6 strong acids: nitric, sulfuric, perchloric, bromic, iodic, and chloric. For the bases, there are a long list of the strong ones, but basically, if you look at the periodic table, it's lithium in lower and magnesium in lower. So if you form calcium hydroxide or nitric acid, that's a strong acid and a strong base. But if you form like something like acetic acid or ferrous hydroxide, those aren't acidic. So the thing about strong acids and strong bases is they don't have these reversibility arrows. So in order for this to be true, we have to form a weak acid or a weak base. So if a strong is formed, there's no reaction. So if the anion here is nitrate and we form nitric acid, HNO3, this reaction doesn't happen because nitric acid isn't formed. This reaction is impossible. If we have calcium and we form calcium hydroxide, that's impossible because calcium hydroxide doesn't form in water. It completely dissociates. But again, if we had something like acetate, acetate is going to react with water to form acetic acid. Acetic acid is a weak acid, so we expect this to happen. And then something like ferrous hydroxide, same thing. So let's say the anion reacts. So we got the anion and it reacts. And let's say the cation doesn't. Well, if the anion reacts, we're going to produce hydroxide. So it's going to make it basic. Now let's say the cation reacts, but not the anion. Well, this is going to form H+. This makes it acidic. But if neither reacts, it makes it neutral. So what happens if they're both reacting? We end up with a double yes column. Well, this is where I say it depends. And what it depends on is how good of a base is the anion, or how good of a base is the anion and how good of an acid is the cation. And you can look these up. You can try to tweeze them out from pKa, pKb data. I personally think that's a lot of work for what basically amounts to an oversimplification anyway. So this is why I say you just need to say it depends. It depends on the relative strength of the anion and the cation for forming their respective H pluses and OH minuses. But if only one of them is reacting, it's clear cut. If the cation is reacting, it's going to be acidic. If the anion is reacting, it's going to be basic. And if neither reacts, it's going to be a neutral solution. All right, buffers. All right, so the buffers homework, there is an example of this on the exam. These are actually easier to solve than they look. So the first one we got HF, and we want to know the mass of HF. What we're shooting for here is a pH of 2.02, and we're given that the pKa is 3.18. So like all these problems, you're going to set up your expression for Q. And your IC table. So we're not given any initial concentration of these, and we're asked to find the mass of HF. So this is basically going to be an unknown variable. It's just going to be some concentration. So we got our minus x, x, and x. So we have a minus x, x, and x. And if we plug into our expression for k, we get x squared all over a minus x, where a is just a placeholder for the concentration of the HF. And if we rearrange all this, we're going to get that a is just x squared plus kax all over ka. But the thing is, we know the pH. And the pH here is the negative log of the H plus concentration. So we can get that the concentration of H plus here is 10 to the minus pH. So actually we know this number. And we know that it equals x. So wherever we see x now, we can plug in the pH, or we can plug in 10 to the minus pH for all x's. And that will give us an expression for A. So now that we know numerically what A has to be, we have the relationship that the molarity of the acid is the moles of the acid or the volume of the acid. And we're told it's a 0.98 liter solution. So if we take our molarity, multiply it by 0.908, that will give us moles of HF, and we can go directly from moles of HF to grams of HF. So that's pretty much how all these problems work. Yep, pretty much every single one of them. You're going to have to put in a dummy placeholder for one of the starting concentrations, but the pH here is going to give you the extent of reaction, and you just need to rearrange your expression for Ka and your expression for Q in order to tweeze out those starting concentrations. Hey, you're welcome. I personally find the buffer problems a lot easier to solve because you're not having to solve the quadratic equation. That said, there are a few that they're asking you to find the pH. And definitely, you can go nuts on these problems. Like they're definitely, if you look at the packets, they'll start asking you for like the concentration of the conjugate base. But it's all the same idea. You just plug in what you know. You still have to go through all of this. The question is now, what's the unknown variable? Why is the bottom Ka minus x? Well, and I just erased all that too. Why is the bottom Ka minus x? So when we get to the expression Ka equals x, x all over unknown minus x, if we rearrange, we get Ka minus x equals x squared. So if we factor it out, aka minus xka equals x squared. This gets pulled over, so we get aka equals x squared plus x times ka. Divide both sides by ka, we get a equals x squared plus ka times x all over ka. But yeah, to cancel out, you need the same thing on top that's on bottom. Other questions? Thermodynamics discussions. I'm guessing you mean the discussion board. So to give me just a minute to copy this all over. And I'm just going to leave off the phases to make it a little bit easier on me. We want PB SO2 plus O2 goes to PbSO4. And I'm just going to leave these as delta H1, delta H2 for now, and we'll stick in the numbers as we need them. So there's two approaches you can do with this. One is to add and subtract. The other is to use Hess's law. We'll start with add and subtract because for this it's going to be really easy. Really what you should be using is Hess's law. That's pretty much always guaranteed to work. So what we need to do is we need to take a look to see where things are relative to the reactions above. So the PbSO4 here is a product on both sides, so odds are we're adding this reaction. The O2 is a reactant, but it's reacted in two reactions, so we just need to keep an eye on it, see where we need to cancel it. The O2 here is a reactant, here is a product here, so we need a negative sign to flip this over. And the lead here is a reactant up here, so odds are we're adding this reaction. So now we need to keep the coefficients the same, it's 1 to 1, so we're probably adding this once. For the SO2, it's 1 to 1, so we add it once. The lead, it's 1 and 1, so we add it once. And this negative here is going to make it look like SO2 goes to S plus O2. So if we work it out, the sulfurs will cancel out. The extra O2 will cancel out from there. So this works. And all we do for the delta H's is the same thing we did to the reaction. So here the delta H equals the delta H1 plus the delta H2 minus the delta H3. The real way you would want to do this is with the Hess's law expression. So for the Hess's law, it's the sum of the products. So the enthalpy of PbS minus the enthalpy of the reactants plus S equals whatever delta H1 is. Here, H of PbSO4 minus the H of PBS plus 2 times the H of O2 is delta H2. Here, the enthalpy of SO2 minus the enthalpy of sulfur plus the enthalpy of O2 equals delta H3. Now, down here, enthalpy of PbSO4 minus the enthalpy of lead plus the enthalpy of SO2 plus the enthalpy of O2 all equals our unknown delta H. So anything that is a pure element or a diatomic gas disappears with zero, as having a zero enthalpy of formation, because the enthalpy of making something from itself at room temperature is zero. You don't gain or anything doing that. So that's zero, that's zero. The PBS is not zero. The sulfur and the O2 are zero. So when we finish it off, we get that the enthalpy formation of lead sulfide here is minus 96.6. The enthalpy of PBS here is minus 123.1, and the enthalpy of SO2 is minus 296.8. So here the lead sulfate, we know what PBS is. It's negative 96.6. So if you add it to both sides, you'll get plus minus 96.6. So now we just have to plug in. Down here, the lead has a zero heat of formation. The O2 has a zero heat of formation. So the heat of formation of SO2 is minus 296.8. And for the lead sulfate, it's minus 923.1 minus 96.6. What I see a lot of students make a mistake on is that this negative will cancel out this negative, so you're actually adding this number back. I think you get something like 722.1 for those problems. But yeah, if you go look on the discussion boards, you'll see what a lot of people do. Usually what I see with a lot of these problems is just algebra errors. And so particularly on exams, I typically give, if the work is set up correctly, you'll get most of the points. Sorry. There we go. Oh, excuse me. All right, if you can go over question 5 for pH from pKa, I can do that. Okay, question 5 is going to look like a dilution problem. So I'll show you how to set up question 5, but you really know how to do the rest of it. So it's asking for the pH if 200 mLs with 0.1 molar ethanoic acid, CH3, CH2COH, is mixed with 250 mLs with 0.01 molar ethanoate. So you got CH3, CH2, COOH. First, we're breaking back into these. And you got your expression. I'm going to list this as HA and A minus, so I don't have to keep writing it over and over again, but we get K equals Q, which is H plus A minus all over HA. And you're given this big icy table. Well, you need to fill out an icy table. Icy. So this part should already look familiar to you. It's this part here that's probably giving you issues. So the thing is that it's giving you volumes and concentrations and they're mixing together. So actually, when you mix them together, it's not 200 and 250. Your final volume here is going to be 450 mLs. So what these two are doing is that they're diluting each other. When they mix together, they're changing each other's concentration. So you need to find the concentration of the acid at 450 ml. So you're going to use the dilution formula, and that's 200 times 0.1. So that's the final volume, that's the starting molarity, and that's the starting volume. And you're going to have to do the same thing for the ethanoate as well. So 450 dilutes to 450 ml. You start with 250 ml and 0.01 molar. So before you can enter these numbers in, you have to use the dilution formula. But once you use the dilution formula, the IC table goes as normal. So that's the point of that problem, is just to kind of get you to see that when you do mix the two together, they do actually kind of mutually dilute. And your pH here will be 4 when you finish. I'm guessing that's the part that was giving you issue. But yeah, you have to use the dilution formula. M1 V1 equals M2 V2. You're given M1 V1 for both of them. The final volume is just the sum of their two volumes. Hey, you're welcome. All right, other questions? See your link to the discussion board. I can check your answers in the discussion board. Just got to give you a minute to bring it up. All right. Why aren't these in order? Oh, thermodynamics. I'm sorry, I thought you meant Hess's law. Thermodynamics. Okay, that's why. Okay, I get it now. Because when I think thermo, I think Hess's law. I don't think. Okay. Okay. So for that discussion board, you're asked to define enthalpy, entropy, internal energy, Gibbs, Helmholtz, and you're asked to specify why P and V matter. And so a common answer, okay, so the enthalpy is usually the easiest one. It's just the heat. And specifically, this is the heat of making and breaking bonds, but it's actually a combination of two things. It's heat plus work. Or I'm sorry, it's internal energy, so it's that U plus the PV, which is the work term for making and breaking these bonds. So if a system is in a closed vessel, it can't do work, whereas if it's at constant pressure, it can be. Now, a common one I see students put here is disorder for entropy. It is not entropy. An easier definition of this is degrees of freedom. Now, in its full definition, entropy is defined as the number of microstates, a number of different ways that you can arrange a system and get the exact same energy. So increasing entropy means that you change the configuration, how atoms are rearranged in terms of speed, rotation, orientation, and still got the same overall macroscopic properties of temperature, pressure, and volume. So that's kind of hard to conceptualize. So degrees of freedom is usually the easy way to see it, is how constrained are the atoms. This isn't disorder. So disorder somehow implies that order exists. You can have high entropy crystals. They do exist. But the disorder kind of falls apart when you compare liquids and gases, because how do you argue that a gas is more ordered, less ordered than a liquid? Neither of them have crystal forms. The molecules really are just kind of bumping around each other. And gases and liquids obey the exact same diffusion laws. So to say that it's disorder really doesn't make sense. And the other thing is that disorder is a completely subjective statement. So the degrees of freedom here are basically how much are the atoms constrained. And this shows up when you look at something like the synthesis of ammonia. So for this reaction, we have two gases coming together to form another gas. So why does this have more entropy than this? Well, the order disorder doesn't make sense because all three of these are gases. But if we look at it, this is what we're starting with, and this is what we're finishing with. So before, atoms were only in pairs, and they moved in pairs. So the only thing that was really limiting each atom was its restrictions for how far it could get away from a second atom. But if we look at something like an ammonia molecule, now this nitrogen has to move in coordination with these three atoms. And so the nitrogen here has lost degrees of freedom because its motion is no longer restricted to just one other nitrogen atom. Its motion is now restricted by three hydrogen atoms, which are two more than before, which fixes the bond angle, which fixes basically how they can vibrate. It fixes the rotational energy. It fixes a lot of things. So this actually has a negative entropy, even though they're both gases. In this case, each atom only has one other atom constraining its motion, whereas in the case of ammonia, they've got three others. Internal energy is going to be defined as basically the energy of bonds in the molecule. And Gibbs here and Helmholtz are going to take a similar form. So Gibbs here is going to be the enthalpy minus the temperature times the entropy, and Helmholtz is the internal energy minus temperature times the entropy. Now, the thing to keep in mind here is that we are sticking to very simple definitions. There's actually a lot more that goes on here. So we can introduce chemical potential. So this is within a phase, these are between phases. So if we have a block of sodium chloride, we can use this expression. But let's say we have sodium chloride in water. Well, the NaCl here can dissolve into the water, and so what we need is a function that describes the energy of exchanging atoms between the aqueous and the liquid, the aqueous and the solid phases. So the better way to think about Gibbs and free energy is that they're the total energy. So if we add up all the different types of energy, so if we add up the heat, the entropy, the chemical potential, or the internal energy, the entropy, and the internal potential, we get a total energy. And the delta here is the change. So going from one state to another. Now, if all atoms are looking to lose energy and all molecules are looking to lose energy. So this is why we get the definition that when delta G is less than 0, we get spontaneity. And that spontaneity is because we've netted a loss in overall energy. Now, we may gain heat, we may lose entropy, but as long as these terms balance each other out and we finish up with negative, it becomes spontaneous, because assuming there's no barrier to go from one starting point to our finishing point, we should have it happen. It will lose energy. Helmholtz is going to take the same line of reasoning. If we lose Helmholtz for energy, we lose energy. That's also spontaneous. So Helmholtz is not the flip of Gibbs. They're the same thing. The big difference between the two is that Helmholtz here assumes no work. Gibbs has work. And that's where this PV definition becomes important, is that for a system and its environment, that negative delta G means the energy had to go somewhere. If we have a positive delta G, we had to get the energy from somewhere else, and this is going to be the environment. Well, if we have a constant pressure system, we can exchange heat and work. So we can change our that delta G sign change, the positive or negative, is going to come across as either work or heat. But for the constant volume, we can't do work. So if we have a negative delta G here, that negative has to be lost in the form of heat, or if we have a positive delta F, meaning that we gained energy, that energy had to come in the form of heat. So it does make a strong stipulation about what that delta G and that delta F become. Now, a component of internal energy can be kinetic energy. Generally, though, we're talking about bonds within the molecule. Your kinetic energy here is actually going to be entropy. So entropy is going to be rotation, vibration, translational. Free energies, those are the most common forms of entropy. There are more, but definitely rotation, vibration, translational. So you can only use, so S is entropy, but entropy is not a it's number of states. Basically, number of microstates that are available. If you're at F, you have to use constant volume, not necessarily, it is constant PV, but specifically it's constant volume. The other case is constant pressure, which is Gibbs. And to the best of my knowledge, those are the only two types of free energy, Gibbs and Helmholtz. But they come up in different situations. Your third thermodynamic pressure is constant. Thermodynamic parameter is temperature. Isothermal operation, I think both Gibbs and Helmholtz are done at constant temperature as well. It's complicated. You had to take a thermo course to really get into the nitty gritty. But yes, Helmholtz is constant volume with no delta PV term, and then Gibbs is constant pressure, and there's a non-zero delta PV term. What they're going to do is they're going to scan in your work and email it to me. At least that's what they promised me they're going to do, because we're not supposed to be meeting in person right now. So when you finish your exam, you're just going to hand all your work over to them. I've asked them to do that because we also don't want the final exam. Like the final exam, we typically keep to ourselves. We don't hand them back. You'll see your grade, but we don't like give you the exam to look at. And what they're going to do is they're just going to scan it all in and email it to me. So once you take the exam, you're done. You don't really have anything else to do. I didn't put a limitation on it. I mean, don't bring like a book. You won't need it. Also, we'll talk about it next week. You're gonna have a formula sheet too that I'm gonna supply you with. Um, so you're gonna get the osmotic pressure, delta T equals KIM. You're gonna be getting all those tables. You're also going to be getting for the electrochem. You're going to be given the Nernst equation. You're going to be given the electroplating equation. So just take a look at that before you start really compiling a whole bunch of notes. This is a conceptual test. A lot of these are conceptual problems. So in terms of notes, there's only so much like knowledge base. There's not going to be that much knowledge based on it. Yeah, we are kind of glad they're going to be emailing us those notes. But yeah, take focus on the exam this weekend, and the next week, definitely tomorrow. Actually, you should be able to see it now that I think about it. So if you go underneath the lessons ribbon, yeah, because I opened up the final exam just so y'all could see the material, but you don't. Yeah, bottom of the page, final exam formula sheet. Because admittedly, you have learned a lot this semester. So the final exam is not a exam of how much did you memorize, more or less how much did you understand. Yeah, if you want to bring your own formula sheet, that's fine. They know that you're allowed to do your own notes. But the thing is, I think you're going to have to surrender your notes. So just keep that in mind when you're doing it, is that when you get done, everything has to be turned in. Yeah, Penderson-Hasselbalch, density of crystals, standard reference potentials. So yeah, if you want to do your own formula sheet, by all means, like that's just considered your notes. Yeah, the only reason I make you memorize all those formulas for the first test is because it's the only way to actually make that test even the remotest bit challenging. Um, test one material was pretty straightforward, and test two is just kind of good to know those kinetic models. What I don't supply you with are the kinetic models for zero, first, and second order. So I would memorize those. I think those are actually useful. They do actually show up. Other questions? See you soon. Yeah, I used to give students the formulas for the delta T, the pi, the osmotic pressure, and all that. The first exams were like 90s and higher, except for people who just literally just didn't do anything in the course. And it was like this false sense of security because then we get to test 3 units super hard. So I started leaving the formulas off of test 1 just as a kind of way to keep students from getting into this false sense of security for like test 2 and test 3, because they do test 1 with a formula sheet and they were like knocking out of the park, and test 2 was just a slaughter. So I was like, let's start setting this expectation that you'll memorize, and then when we get to the final exam, we'll back off that expectation. So it's kind of social engineering more than anything else. And I'm not happy I have to do it, but I think it's better to not. It's better to set that expectation early and then relax, and then the reverse of not set it early and then have to say, okay, now you really have to memorize a whole bunch of stuff. All right, I'll give it about another 3 or 4 minutes. It's showing 0 concurrent viewers on my side, so everyone's done with questions. Again, just make sure you're taking your exam, but I'll keep it up for a few more minutes. But I think we'll probably cut it off a little early today. All right, no other questions. Again, these are just office hours. They're not lessons. They're not lectures. Good luck on your exam this weekend. I know we're going to turn around and take a final exam right next week. It's a tough pace, but we are here in the home stretch. All right, if you have questions, please feel free to reach out and email me. Otherwise, I will see y'all next week.